So, so the key is on parallel circuits that all of our voltages are the same. All right, because as we move through our wires here, we're not dropping any voltage across the wires. Our wires are ideal, and so because all our wires connected across top and bottom, and we may have no drops across the top or bottom. All right, and so our 12 volts runs across this whole circuit, and so when we and that makes it very easy to do these calculations. We've got 12 volts on each resistor, then you use Ohm's law on each one. You can get the current through each one. Then you can calculate the power in each one, which I did in red. And then I guess the question is, how do I figure out the current through the other branches? So I've got this current through these parallel branches. But what about in between? Like what about right here? What about right here? This current I3 goes through this whole branch at the end. All right. And then what about over here? How do you get those currents? Well, use water in a pipe. All right. So I've got water coming through this pipe right here. All right. And it's going to branch. It has two branches. It'll branch two ways. And I already know that 120 milliamps branches through R1. All right. And then the remaining water continues to flow here. And then that branches. And those two branches, I calculated, I've got 60 milliamps here, and I've got 40 milliamps here. Well, if this splits into 60 and 40, then our total here must be what? It must be 60 plus 40, because that 60 plus 40 is what splits. All right, so our current through this bottom branch here must be 100 milliamps. Okay? Well, if that's 100 milliamps, let's move backwards here. I had my source current that splits into 120 milliamps going up and 100 milliamps going over to feed our other two pieces of the circuit. So our total current must be what then? What's that current mean? 120 went up through here, and then 100 went to the right. So our total must be how much? It's 120 plus the part that's going up plus the 100 that's going to the right. So we should have 220 milliamps. All right. Same thing when this current comes back around here. We've got 40 coming around. We've got 60 coming up through. They should add back together to get to 100 right here. And then that 100 should join up with this 120 coming right here into 120 plus 100 is 220 milliamps. All right, so it's water joining back together and then flowing back through again. All right, this is what we're really using something called Kirchhoff's current law, KCL. So Kirchhoff's current law says the sum of all the currents, this Greek letter here means the sum of all the currents coming into a node. And I've actually shown you my nodes up here. I've got 4 nodes that I've put up here, A, B, C, D. Those are those joints where you can split or come back together on, all right? So you can take the sum of all the currents into a node equals 0. All right, does this work? Let's just try it out on node A. So node A, so we should have the sum of the currents into node A should equal 0. Well, what currents are going into A? Well, I've got 220 milliamps going in, all right? What else do I have going in? Nothing else. I got stuff coming out. Well, so what do you think stuff coming out is? They're negatives. Minus 100 coming out, minus 120 coming out, that should equal 0. Does it equal 0? Yeah, it equals 0. All right. So there's an example of what Kirchhoff's current law says. But it's logic, all right? It's water in a pipe type of logic here. Okay. So let's I set this circuit up right here. And you can see I laid it out. So you come on up close here, everybody. I got parallel, parallel, parallel. All right, my 100, 200, 300.
Right here.
So let's measure some voltage off of this.
You don't think what? Me and Pat saw the other night, soldering, and I'm like, yo, I was holding things in place, but didn't know vice or anything. Like, just press the solder in when I heat it up. He's like, word, I got you. And I'm like, I'll tell you when to stop. And he pushes it in. I'm like, all right, that's good. And he's like, okay, awesome.
So I'm measuring voltage at my source. I'm measuring current. I inserted my.
The solder? Yeah. It worked fine. Like a glue gun. He just kept pushing the glue through.
So I inserted my ammeter. You can see here, goes through here, it comes back out. So I inserted my ammeter up top here, right here, and right now I'm measuring my voltage right there. All right. And we're going to set my ammeter. Now this it should have 0.22 amps, right? 220 milliamps. This scale down here only goes up to 200 milliamps, and so I can't use that. So I'm on the 10 amp measuring circuit, at least for this one. I can switch it down to the lower ones to see these three individually if I wanted to. And so I've got 0. I'm going to turn on my power supply. So we're a little bit high on my voltage. I'll bring it down a bit. So there I am around 12 volts. And my current is 0.22, 220 milliamps. It works. Now, let's measure the current in a second spot here. Let's measure it through this first one here. And let's take this out now. And so I'm going to allow the current to flow through here and then back out through the bottom. All right. All right. So now my voltage is coming across here. Here's positive 12 volts. Here's the black wire at 0. You notice I'm color coding these things. All right. Typically, it's red for the hot part of your circuit, the high part of your circuit, and black for the low part. All right. So everything along this line is at 12 volts. Everything along this line should be at 0. Or if I touch across these wires, I'd see my 12 volts. And I just inserted my ammeter, right, coming right through here. And what am I getting? I'm supposed to get 120 milliamps. Am I? Yeah, it's 0.12. Now, this is actually within my range, so I can switch on to the lower scale. So I'll do that. I'm going to pull this out. I'll bring this down to 200 milliamp range. And so there you see, I'm at 123 milliamps. All right. And what's my voltage showing up here? 11.93. So actually, if I increase this voltage, what should happen? That number's going to go up a little bit, right? Hey, look at that, 12.00. All right. Why is that off a little bit? Why is that up 5 milliamps high? Why is that too high? I mean, this is 12 volts. 12 volts here, so we have 12 volts the whole way. Why is that number a little bit high? It's almost if I have additional voltage there. Or
That's showing the resistance.
This is voltage, and that's on voltage. That's current. So why is that showing a little bit more current than I should have? 5 milliamps extra. On our resistors, right? That means our resistor is probably a bit low. We'll check it and we'll see. All right. Now, so that seems to be working. Now, I also calculated power on each one of these things. So we're on resistor 1 right now. The power I calculated was 1,440 milliwatts or 1.44 watts. What are these resistors rated for? A quarter of a watt, 250 milliwatts. So Are we safe or not? Or is this dangerous what we're doing here? Yeah, we're supposed to be running this at 250 milliwatts or below. So we are almost 6 times above its rating. All right, and so so in other words, if I were to touch this, it's hot. You can try to touch it real quick, like an iron type of quick, and it is hot. Don't hold it on. Don't hold your finger on there. It's hot.
Oh, yeah.
Yeah,
So if you leave it like that.
try it out. Yeah, try it out. Yeah.
If you leave it like that, will it after time?
Ah. I got $1.
Try it out.
for a
Try it out.
Well,
Would you try it, please?
Fine. Nate, if you lick it, I'll give you $1.
All right, see that? Now, if you look, what about these other ones? Resistor 2, I had running at 720 milliwatts. That's 3 times. All right. This one's at 480, which is about twice. All right. But you notice that's the ratio of our currents as well going through there. So this one is double. So let's see what this one feels like. This one I can hold my finger on before I feel it. Try that one.
all 3 at once.
This one will burn you immediately. This one takes a moment before you start feeling it.
Slow burn.
There's like 3rd-degree burns and 1-degree burns. So what happens?
I guess I kind of.
Versus what you were doing over there, you had like 50 times more than was going through it. It's crazy over there. Yours literally turned black and they were smoking. Right? And if you put your finger on it, you get an instantaneous burn on your finger.
Would this one end up smoking after a while?
Is it changing its color?
I thought it was.
It's.
After a while.
Yeah, I would say if you look at the color on here, I think the color of this is darker overall, and these are all painted up the same way. See how its tan finish is a little bit darker. So I think it has as compared to those two.
So what's wrong with sending 6 burns? So what's gonna?
It can't dissipate the heat, so it's you're destroying your materials, So, and in worst case, it'll burn through it. Or worst case, it starts a fire, and melt and you can injure somebody, starts a fire, whatever. So you pick the wrong resistance, or for some reason there's some other error elsewhere in the circuit which is pushing too much current through here, and so you have a flaw someplace else which is overloading someplace else, and you'll get some sort of cascading problem with failures. All right. So that's that. So we've tested that circuit. That works. All right. So what else is there to say? Now, equivalent circuit. So I also looked at this. Now, on the series circuit, I started with the equivalent circuit because it's very easy to conceptualize. If I got this one resistor after another, they just add up. And from that, we got our current. And from the current, we were able to figure out our voltages and all of our powers. So we sort of tackle these from opposite standpoints, series versus parallel. So when you have your quiz on Monday, you will do these same things. So you're gonna study these, and you will do the same thing. All right. So your equivalent circuit here. So my equivalent circuit is replacing these 3 resistors with a single resistor. So the battery wouldn't know the difference between one versus the other. And remember, for a series circuit, it's easy. It's add the resistors together. For a parallel circuit, you got to add the reciprocals and take the reciprocal. So I've got 1 over 100 plus 1 over 200 plus 1 over 300. If you like fractions, you can get a common denominator on these in the bottom of 600. And I got 6 plus 3 plus 2 over 600, which is 11 over 600. And take the reciprocal of that. I got 600 over 11 is 54.545454 repeating. Or I could just toss this all in my calculator at once, and in the end I get the same thing. And then I took I found out the total, my source current is just my source voltage, 12 volts divided by my 55 ohms. So when I do that, I get 0.22 amps. And sure enough, it was 0.22 amps. So these two calculations match up. All right. Okay. Easy as that. Now, what you need to do is you should go through your lab packet, because we've talked about how all these circuits work, Now you can go back to your lab packet and go back through your observations and conclusions, and you can fix those. All right, because now you know how these circuits should be working. You'll have a better understanding of what was going on in your circuits. All right, so on Monday you should have that packet ready to turn in for a grade. All right, you will be able to use that packet and your notes to do your quiz if you want to, because this is an open notes course. This is not a closed notes course. But what I want to talk about is I want to go to the other thing we did is batteries, and Nate's already way ahead of me here. Is his battery handout. So let's flip over to our battery handouts.
Are we going to talk about what the difference is between a AA and a AAA? Because I have no idea. I just know that they're different sizes.
Yes, we're going to talk about that.
What's the difference between a AA and a AAA? Tell me. That's the only difference. It's the battery company trying to make more money off of it. Everybody's stockpiling on AA's. What do we do? Make things that require another one. Make things that require AAA's.
All right, so you guys went through some battery tests here. The first thing I had you do is I gave you had a couple 9-volt batteries. One was a fresh one was a quote-unquote dead one. The dead one still measured a voltage. Say, yeah, this still has 5, 6, 7, 8 volts in it. So why can't I use it? So what happened when you put the load on it? To the voltage. When you put the load on, what happens? It dropped. All right, the voltage dropped. On the fresh battery, you put the load on it. It might have dropped a tiny, tiny little bit. All right, so just because a battery reads voltage doesn't mean it's a good battery. It should read something around what we call its nominal voltage. All right, a nominal voltage is the voltage that's printed on the side of the battery. Like 9-volt battery should be around 9 volts. In fact, a very, very fresh 9-volt battery, you can read as much as like 9.3, 9.4, 9.5 volts. Okay. And then I asked you to put the batteries in series and parallel. I think now we have a better idea, knowing what series and parallel does, to predict what's going to happen in here. All right. Let me just flip over to this. We had these 10-energy batteries, right? And so my question is, when you put these 4 batteries in parallel, and here's the nominal voltage that it's showing you, 1.2 volts, and these are AA batteries. So the nominal voltage is let me just grab a couple batteries here. Nominal voltage of this is 1.2 volts. The nominal voltage of this Duracell, let's see what it says on here. It says 1.5 volts. So one question is, why is this 10-energy battery 1.2 volts, and why is this Duracell battery 1.5 volts? And I also have these Everready batteries, and you would see the same markings on these. So here's this Everready AA battery. It says on it, AA size E91, LR6, AM3. So there's more AA, E91, LR6, and AM3 are all the same meanings for this type of battery, this package size, okay? And on it says 1.5 volts. So my Energizer here, my Duracell, they both say 1.5 volts labeled on them, and the 10-energy says 1.2 volts. Why? What does that mean? And see if you feel any difference between these, just in terms of their size and mass in your hands. Do they all feel the same? So, Patrick, what did you say the difference was?
5.
You can to some extent, just not very much. But what's different? Ultimately, what's different inside those batteries? And when you say the composition, you mean the chemistry, all right? Different chemistry, different chemicals inside, all right? And you guys studied electrolytic reactions and stuff like that. Different combinations of chemicals give you different voltage differences, all right? They give you different voltage potentials, is what we call that. All right? This is what we call a nickel metal hydride, all right? So part of it is made out of nickel. Part of it's made out of some sort of metal hydride, so some sort of hydrogenated metal, all right? So this has a different chemistry inside than our what we call our alkaline batteries, all right? And so the chemistry is what defines what our nominal voltage is, and the chemistry also defines whether it's rechargeable or not. What other type of rechargeable batteries are very common? Made out of what material? Lithium ion, all right? So lithium is what type of material? Lithium is a I need my table of elements. It's over in the other room.
What'd you say?
It's a metal. It's an alkali metal, all right? If on the chemistry on the chart, but it's very interesting because it's a third element on the table of elements, so it's a very lightweight element in terms of its material composition. But it turns out it has very good properties for a battery, and that's what you see most batteries now in modern electronics, because it holds more. It has the capability of holding more charge. I have a chart coming up here. Now, so we've got different types of batteries. So we'll have, depending on the chemistry, you'll have different nominal voltages. So this nickel metal hydride technology, whatever that chemistry is, that chemistry dictates that it has a 1.2 volt potential energy difference in the electrical potential energy. All right? So my question is then, if I put these things in parallel, what would you expect the output voltage to be?
Just one battery.
You'd expect it to be what? What happens in parallel? I didn't ask for a sentence. I asked for a number. It should be the same voltage in parallel, right? Everything's the same voltage. So our output voltage here should be 1.2 volts nominally, all right? If they're fully charged, it'll be a little bit higher than 1.2. If they're partly discharged, it'll be maybe a little bit less than 1.2. If they're very discharged, it'll be very low. All right. But so we'd expect, though, from our knowledge now of what parallel circuits is, these should all have the same voltage. So putting a whole bunch of these things in parallel, does that increase your voltage? No. So what advantage does that do for you? What advantage does that give you? Think about that. All right. Let's look at series. So now, instead of parallel, I'm going to stick them in series. What happens when we had the resistors in series? It adds up. So we'd expect 4 of these put in series would add up to, which is, the nominal voltage should be, well, you're slow today, aren't you? Well, you are slow today. There it is. He's normally on top of these things like that. His brain is not working today. 4 times 1.2 is 4 times 12 is 48, right? So this should, normally, this should be at 4.8 volts. So this one gives you a lot more voltage. That seems like a pretty good deal, right? And we know from when we're doing our little project we had some motors and stuff for driving, we could add additional battery packs on in series, and by putting in, I could use one battery pack for 4.8, 2 would get me 9.6, and so on and so forth. And so sometimes we use 2, and for Zach and I, we used actually 3 battery packs because we needed a higher voltage to get our motors to move faster. So a higher voltage, certainly we saw the advantages of that before. A higher voltage will make your lights brighter. In fact, we had to, for Aaron and somebody else, who had I think you two guys, right, both, you had light bulbs, your little light bulbs you were testing. If I put 4 batteries on, I was burning out the light bulbs. It was too much voltage. So we actually were able to drop down to 2 of these batteries rather than 4 in series. All right, so we didn't need all that voltage. Remember, voltage is a measure of your potential energy, how much energy you have stored ready to provide. So the taller that hill, the more current you can push through. All right. So by stacking these, we get a higher hill. So you can think of these. I should have done this vertically, so you see a taller hill. And then we can drop off electrons off those hills. It'll be faster down at the bottom of the hill. All right. So that's what's happening. Voltage is like a potential energy hill. You raise a ball to the top hill, drop it, it's going to be faster down at the bottom. Same thing for electrons. If I have a taller voltage hill, I drop off the electrons. They'll have a higher speed going through. Higher speed of electron is higher current. Okay. And higher current gives you more power. Okay. So the advantage to having 2, 3, 4 of these in series is that what happens? Our voltage is add. So that means our potential energy is higher, which means our current is higher, and our voltage times current, which is power, is higher. All right. We double the number of batteries, we double the number of current, and double the number of power.
But they die out faster.
All right. So why?
Because you're using all 4 at once. In parallel, you're using basically 1 at a time, technically, or you're using 1/4 of the battery at a time.
Yeah. So I got to give you 2 bonus points for that. That's really good. So essentially, when we have these things in parallel, what's inside of here? It's a pot of chemicals. I got a pot of chemicals, pot of chemicals, pot of chemicals with a lid on it, lid on it, lid on it. It's just basically, instead of having 4 pots here, why don't I just put them all into one big pot and stick 1 lid on it, 1 bottom on it? And then I'd have a much bigger chemical well to draw from. Would my voltage be any different, though? No. So that's essentially what's happening here. So what's the difference between a AAA battery, a AA battery, a C battery, and a D battery?
AAA is less power. Holds more hot. Then you get the
So I'm going to lay out some battery sizes here. Where's my AAA batteries?
They just hold more power. They just hold more energy. More chemicals, more power.
Yeah, I mean, AAA to AA, and so on and so forth. Let me get a AAA out here. So the difference between a AAA and a AA, or a C and a D, is just how much chemicals they have in the package for you to draw from. All right. So if you look at this, I'm comparing a AAA to a AA. The height difference is, I don't know, maybe 10 or 15% higher. The radius is probably doubled. Right? If we double the radius, what do we do to the volume? We double the radius, the cross-sectional area quadruples, so our volume quadruples. All right? So this should have about quadruple the AA should have about quadruple the stored energy of the AAA, roughly.
So is the AAA just used so that where you boil batteries can be smaller? That way you can make things more condensed.
Yes.
That's the only reason.
Yep. Yeah, you don't have enough room to put your batteries. You have a smaller package. So I need, these are in series, so they want on my TI-83 calculator, TI-84 plus calculator, I have 4 AAAs in here. The only reason I don't have AAs is because I'd have to make my case bigger. So it's a matter of convenience. It's a matter of convenience of size. How big would your calculator have to be to put 4 Ds in here? But it's a trade-off, right? How long do your 4 AAAs last in your TI-83, 84 calculators?
All 4 years. I've had all 4 years.
A long time. So you could probably go down to the next size, but the next size isn't really commercially available, right? And you would save yourself the size in there. But that's the size that fits, right? On your phone, what size battery you want on your phone? I mean, do you want this to last a long time? Do you want it to last more than 6 hours?
Yeah.
How many people don't last a whole day for the charge? This one I could run for 2-3 days on a single charge. This is pretty good. It depends what you're doing, right? If you're watching video, forget it, all right? But if you're just using going back and forth a little bit. Your screen is what's really drawing your power. Your screen, number one, and then your microprocessor, what it's doing, it's the type of microprocessor. Yeah, then there's other things that are constantly bleeding your energy. If you have your Bluetooth on, if you have your Wi-Fi on.
Your phone's always roaming, so it's always looking for a signal.
Yeah, so, and if you have your network on. So there's 3 communication devices on here, and your GPS, 4 things that are on in the background. And you could turn all those things off. Turn all those things off, then it's a computer, not a phone. Right? So.
Yeah, but if you're ever in a dead location, your battery will drop. You're constantly looking for a good signal.
So.
Very low, like New Hampshire, you're constantly looking.
In any case, so that's the difference. Now, so here you have this chart. You should look at this chart. I've got different battery chemistries on here: lead acid, nickel, cadmium. This is what we call NiCad. This was the in the 80s and 90s when they started coming out with rechargeable batteries. This was the first type they had, NiCad, and then which was pretty toxic material. So then they switched over to nickel metal hydride. All these things, the lead acid, which has lead in it, which you don't want to toss in your garbage can. Lead is very toxic. Nickel not. Nickel and iron are the 2 most common elements on Earth. You don't realize that because the core of the Earth is pretty much made out of those. And they're pretty neutral. Cadmium is not so. The nickel metal hydride is something you want to recycle as well. You'll notice there's a voltage. One battery, one cell is worth 2 volts, 1.2 volts, 1.2 volts. Here's my alkaline batteries. Alkaline battery is not toxic. You can throw that away, and that is decomposed in the environment without any real issues. Lithium ion is 3.6 volts for one cell, different chemistry. And then a newer version that's coming up is lithium polymer. All right, and this shows you how much. It gives you some nice summary of the data, what the cost of each type of material is. So the upside of alkaline is they're cheap batteries, very cheap batteries. The batteries, different types of batteries can only allow current to be drawn out at a certain rate, all right? Because essentially that tells you that there's an internal resistance in the batteries, essentially, all right? And so if you want a whole bunch of current really quick, some of these batteries can't provide a whole bunch of current because it can only push out current so fast. So essentially there's something resisting the flow of current inside the battery. You can model it like that. Lead acid batteries have, and hold on, where are we here? Lead acid batteries and NiCad batteries had very, very, very low internal resistances. What do we use lead acid batteries for? Cars. All right, so car batteries. All right, and do we need to pull a lot of current out of car batteries? What do we got to do? We just got to run the lights off them, our radio, nothing, right? How about starting the car? When we start the car, that's when we're pulling a huge amount of current to it. You have 700 cranking amps. You're pulling a huge amount of current when you're turning over your engine. Yeah, you have when you have your battery running, your alternator is actually recharging the battery when you're driving your car. All right. So when you're driving it, you're recharging it, and then when you're sitting there, well, and how long do you hope your battery in your car, if you have it sitting there, if it sits there for 2 days, it'll still have its charge? After 2 days, your car dies. I'm talking about a normal situation. What about your phone? If you left your phone for 2 days, dead, right? So you have, so if you look at this, self-discharge is how much does it discharge with nothing connected to it? It will sort of bleed off its energy into its surroundings slowly. And lead acid batteries have a very low leakage. So do alkaline batteries. That's why the alkaline batteries is like 0.3% per month. So that's why these have a very long shelf life on here. Yeah, that's why they can actually calculate an expiration date when you're lost so much that they're sort of worthless. All right. So long shelf life, very cheap. That's why these are great. And what's your energy density? How much electrons can you store in there to allow for your chemical reaction to happen? That's down here. Lead acid batteries, 70 to 110. NiCad's a little bit better. Nickel metal hydride is a little bit better. So this is like per gram of material, how much can you store in it? Alkaline jumps up. So alkaline, very dense, very cheap, high shelf life. So alkaline batteries are pretty nice. Lithium ion, even higher energy density. Lithium polymer, even higher energy density. So longer battery life, right? So ultimately, you'd want something like this in your cell phone that has a very high energy density. Plus, the other thing you want to be able to do is want to be able to reuse it. So how many times can we charge this? All right. So lead acid batteries, we can recharge 2,000 times, 1,000 times, 800 times. Low. So maybe you can recharge an alkaline a few times before its chemistry gets messed up, so you can't do it anymore. And then these batteries are rechargeable quite often as well. But car batteries, you want those to last a long time, right? So they can be recharged many, many, many times. They have low cost, relatively speaking, low internal resistance, so you can pull out a whole bunch of current out really quickly, all right? So that's a comparison of these different batteries. Now, what's a 9-volt battery? What chemistry does that have? Do you see a 9-volt on here? You see 9 volts on there? What kind of chemistry is that? Yeah, so what? You can get rechargeable 9-volt batteries. Where's the 9-volt on there? It's a lead acid. So you think you're going to have lead acid batteries all around with your with 9-volt batteries? So I got lead acid inside of both of these things, just ready to leak and destroy everything. Back in the day, that's what they had, right? They were using lead acid in pretty much everything. So batteries were sort of dangerous.
I'd say alkaline or nickel CD.
They only go to 1.5 volts though for alkaline.
Oh yeah. Oh wow. Okay, yeah, that makes sense. It's just more cells.
How many?
4, 5.
Oh wait, hold on. I got a C cell here. Putting our line up.
6 cells. 6 cells in the 9-volt.
Oh, you mean that? You guys ever opened up a 9-volt battery before?
No. Yeah.
There it is.
Wait, that's the inside of a 9-volt?
Yeah.
I think that gets me bonus points, Mr. Ryan.
Oh, I only had to lead you to the whole conclusion there. Here's another variant of a 9-volt battery. And what do you see here? This is 2 pieces. This will come apart. How many cells? 6 stack cells. Those are 6 side-by-side cells. So these cells are sort of set up cylindrically like these guys are.
This battery is in series.
Those are in series.
Yeah.
And those are slightly smaller than a AAA. So maybe that's a quadruple A. I don't know. How many volts?
Why?
This is an A23 cell.
Does that mean A raised to 23?
I don't know. They have all these crazy numbers for things. I have these little multimeters at home that use this size. It's a crazy size. I had to order online. This is 12 volts. That's a 12-volt battery.
So it's just got a lot more. It's got like 12 cells in there.
It's got 12 cells.
No,
what kind of reaction are you talking about here? 8?
Yeah, probably
8 cells.
Do the math here.
Yeah, 8 times 1 is 8. 8 times 5 is 4. 8 plus 4 is 12. 8. 8 times 0.5 is 4. 4 plus 8 is 12.
What's 6 times 2?
Okay.
I got 6 of those.
Yeah,
all right. I got 8 of those.
Yeah.
What's inside of this is several of these button cells just stacked up. All right, that's what's inside here. There's several of the button cells stacked up. All right, so there's several button cells just stacked up end over end in there. Some of these button cells, they also have mercury in some of these things as well. The button cells, you got to make sure you recycle. Don't throw them away. It depends on the button cell. And the button cells come in larger and smaller sizes.
I don't have a button cell, but I have that blue battery. So I just cut the battery open and take out the cells. It's basically connected by wire.
So what I want you to do here, I want you to, we know AAA, AA, there's a C cell, there's a D cell rechargeable. Here's a D cell that's an ever ready.
What is that?
That means it's an ever ready.
It's always ready, no matter what.
Apparently.
Forever.
So I want you to I'm going to pass these down one at a time, and I want you to tell me if there's anything wrong here. All right? And these are, well, I'll just pass. These are all supposed to be alkaline. All right? I want you to tell me if there's something wrong here. Ready? Just take a feel of it. All right? Just take a feel of the weight and pass it down.
It feels light. Compared to the one you showed me before.
Are these all full charge?
Just feel the weight of it.
What? Wait. Oh, they're all dead.
What?
Wait.
Now, are they all
Pass it down, would you please?
full charge?
Does anybody notice any problems here?
It gets bigger, but it weighs
heavier than the heaviest one. The biggest one.
What's wrong?
big
That big one. There's something wrong here.
Dead.
By the way, I have some copper tops at home, and they don't feel like that. Get some tools here, see if we can rip one apart. All right, give me the battery. Let's see if we can rip that sucker apart. Give me that ever ready. Where's that ever ready?
All of them are.
Because this does not feel heavy enough. Oh, by the way, here's another one. Ready? This is a rechargeable.
That sounded light when it hit the
So this is probably a nickel metal hydride rechargeable. You tell me if that's full of chemical.
Oh, it's made of styrofoam.
What the hell? It's dead.
How do you know if it's dead or not? You can't tell if it's dead from the weight.
You can't.
What the hell kind of statement is that?
If you drop a battery and it doesn't stay up and it goes like that.
Okay, old wife.
I'm Einstein, dude.
Okay, old wife.
Could it be the cable being planted too?
Then why wouldn't it fall this way? So why would it fall that way?
Maybe you're dropping it unevenly.
Drop it from the battery. My dad
I'm taking away your bonus points, by the way, for saying stupid things like that.
That's a genius, Roy.
So let's just see what's in this high quality battery here.
What?
Ross talking about dropping toasters and that.
Shut up, Aaron.
Oh. We got layers upon layers of subterfuge and
I'm a genius. I make toast while I'm taking a bath.
I'm telling you, I'm Einstein up here, but as soon as Aaron should know that.
Oh, yeah, you're a great painter, but right when
While I'm ripping this apart, let me show you some diagrams of what's inside batteries. Here's the charge-discharge pattern. Do you have the slide? So what happens is your nominal voltage, like you guys had the Tenergy cells, the aqua-colored ones, what kind are they? What's the chemistry? They're nickel metal hydride. So, and NiCad and nickel metal hydrides are shown to show the same performance. And they're showing some other types of batteries here. They got nickel zinc. This is the nickel zinc ones are that's nickel zinc is the alkaline batteries. So this is alkaline. You might want to label that on the sheet. In other words, label it on the sheet. Okay? So, and you can see, here's the nominal voltage is like in here at 1.5 volts. A little bit higher than 1.5. When these come fresh off, they're about 1.65 volts each. All right? But you can see when you start losing your charge, you reach a spot where you sort of drop off. And when you put a load on over here, it pulls it down to zero. All right, which I had you guys doing. Putting a load on over, and in this case, it should keep it up this level. You put on a load over here, it's going to pull you way down. Okay, so what's the difference? You know the difference now. There's a nice picture of some different types. Here's what's inside battery, a little diagram.
Is it just one battery?
All right, screwdriver. So you can see they've got this is the working part of all this chemical stuff in here, and you've got a carbon post here connected to a terminal up top, and you got a terminal bottom, and you've got a sheathing around it, and you've got an interchange that happens in between them.
That looks like a
There's another diagram of it.
Nice. The rod.
Here's a lithium-ion battery. What'd they say back here? There's a cap sticking on top of an electrode. There's my electrode right there. Here's the cap that goes on top. But I want to know why this thing is so darn light. I've got an outer metal shell. There's my outer metal shell. And here's my material inside.
Pretty sure that's not safe.
Whoa, stuff is falling off, man.
There's my material inside. All right.
Carbon.
It's like carbon-like stuff that's like a damp powder. All right.
Moist powder.
But this isn't too heavy. I mean, the ones that my copper top ones I have are a lot heavier than this. So this is a cheap version of a battery. My copper top's way more than this. So there's some other material compositions which are denser and have longer life. Now, if you touch that stuff, you ought to wash your hands because it probably is alkali base, right? So it's a base material, not a. And this is just showing how they layer things together to create these other types of batteries. Lead acid battery. A lead acid battery has 2 volts per cell. So we have how many cells? 6 cells. 6 times 2 gives you 12 volts. Motorcycle batteries are 6 volts typically. So you have 3 cells. All right. And what's inside a 9-volt battery? And that's what we just saw. Right? Okay. So voltage. Just a couple little odds and ends here. All right, we've talked about that. All right. So for Monday, you should have your lab packet completed. So finish up any measurements, finish up your explanations. You should know everything now. You should be experts in this. And I'm going to give you a quiz on series and parallel circuits. You're going to work out the same stuff you've been doing on the homework. So nice job for doing on that homework. Do it on your final piece.